Ja, WiNoDa Knowledge Lab, it's in German, meaning Wissenslabor für naturwissenschaftliche Sammlungen und objektzentrierte Daten, which means in English, the Knowledge Laboratory for Natural Science Collections and Object-Related Data. And I will just briefly go into details of this. To make it clear, we are an educational project, you can see it this way, which brings together 6 different institutions across the country, mostly localized in Berlin and Potsdam, but not only. And the leading institution in WiNoDa is the Museum für Naturkunde, so the Museum for Natural Science History in Berlin. And this is a home for more than 30 million objects. This is a very impressive number. And each of these objects contains answers to questions about the history of the Earth, of biodiversity, and of humankind. But to extract these answers, researchers need to be able to work with the data coming from these objects. And this is where we come into play. So we teach or help researchers to work with this object-related data. What does it exactly mean? Object-related data are all different kinds of data associated with objects, with one object. And as you can see here in this example, if you take this bag, for example, you can see that there is literature data, there is genomic data, ecological, biochemical, historical data, there are geographical data, all associated with one and the same object. And to work with all these varieties of data, researchers need techniques and methods. We also have an archive, which makes it interesting not only to people from natural sciences like biology or genetics, but also to researchers from digital humanities and, of course, to data scientists. Yeah, and here we are, WiNoDa. As I said, we help researchers to work with all these kinds of data, primarily by teaching. We organize courses on topics, like, for example, applied data management, working with databases, automatic analysis and processing of image and text materials. Now you're here because you subscribe to our, or you subscribe to our webinar series, Data Science. And we are also organizing soon the workshop on scientific object digitization. We are also planning summer school, data acquisition in the field, course on DNA sequence analysis, and much more. So you can see all variety of data covered by our courses. And just follow us to stay updated on future events and news. Here's a website, and we also have a newsletter where we send our updates. And we also have a LinkedIn profile. I'll put all the links on the chat, and you can click on them later and subscribe. Now, a few words about the webinar series Data Science. Here we are, and it will take place every second Tuesday from 12 to 13 Berlin time, and it is in English. And he's our lecturer. Yeah, we are welcoming Dr. Tim Konrad, who is the head of the Visual and Data-Centric Computing Department at the Zuse Institute Berlin, and also the head of the Medical Bioinformatics Research Group at Freie University of Berlin. And the webinar series starts with 6 events all around data science. Today we have Introduction to Data Science. Then we'll continue with the topic of machine learning, divided into 2 sessions. One session is a brief introduction, and the second session is a hands-on part. Then the same structure for the deep learning topic, brief introduction, and another session is a hands-on session. And then we'll finish with the data visualization with Python, both introduction and hands-on parts together. You would need to subscribe for or register for each webinar separately if you want to participate. I'll also paste the links to the chat. And now the floor is yours. Tim is our speaker.
All right. Then, thank you for the introduction of our program and about at least my name and title. I will not go actually into much of self-advertisement or anything about the Institute because I don't think that belongs here, at least today. And let me get my screen ready. You should now actually see the slides. If at any point in time I'm too fast or mumbling or the audio quality becomes worse, please just scream at me because I might not see actually everybody. Also, I will not check the chat in between. So if there's something you have as a question or so, please directly unmute yourself and ask because it's a little hard to have all these things monitored at the same time. Good. Here's my contact details. If you have questions later, please don't hesitate to shoot me an email. Zoo's Institute, you might or might not have heard. We are a research institute owned by the state of Berlin, mainly at least. We are having mathematicians, data scientists, computer scientists, a lot of theory people or practical people. And that's one of the points why we also in this project, we're having a supercomputer in the basement where a lot of these data science or analysis and so forth can be done and will be also an asset to this WiNoDa project. Good. So let's move forward. This we just heard, these are just the dates again. Important from here is only that today we're having introduction to data science. Since I'm not really sure how the audience is or wasn't sure how the audience will be, I kept it super general. Just in case you're already quite familiar with data science, you might want to do something else now. If you just heard the name of data science and are not really sure what might be there behind, then please stay with me. Once again, always in between, just unmute yourself and ask questions if there are any. If I don't hear anybody, I just assume everything is good and will continue. Now, first part of data science is obviously data. And to just give you a rough idea about what we mean or people mean, or I mean maybe in particular when we talk about data, is to just imagine a day in your life. And you can imagine, whoa, what is the best road to take once I want to go from A to B? I want to go to my workplace today, or I want to go shopping and I'm not sure whether the road is blocked. Or is there any bad weather today that I can expect? Or you're even going further and say, wow, I just found this money somewhere. How should I actually invest it? What's the best thing I can do today? How's my health even? And the only thing that this should tell you is there's a lot of things that people are thinking about on a daily basis. And the point is that more or less all of these four questions, or the answer to these four questions, can be improved or optimized if you would have access to all the data that are connected to it. So if you would know about all the traffic information that is currently on the road, you would know how to optimize your route. If you know about all the weather conditions that are currently around you and everything that's happening from rain to whatever in the next couple of seconds or minutes or even hour, you know what's happening. If you would know about the whole situation of economy and of what's also happening, maybe a particular, well, you get the pattern. Health is even in particular more important if you had access to all the data, say, about your body, not only blood pressure and pulse and these kind of things, but maybe even to all the molecules that are floating around the body at this particular point in time. You can or could, of course, make different decisions about the health, for example. And quick answer to that, most of that is possible these days. We are collecting data in unbelievable amounts. There is another major driver at the moment, which is called the Internet of Things. Actually, not at the moment, also quite an old topic, but it's speeding up as we speak. And the main idea here is that there are sensors everywhere. And when we talk about sensors, it's not necessarily only about, say, fitness tracker, wristbands or so, or sensors that are on the body that people can be tracked, or sensors in your home that might measure or set the temperature according to what you want. It's literally everywhere. There's sensors in your fridge. You can buy blankets with sensors that keep you during the sleep in a particular temperature, and it measures also body temperature. You can have it in a chair, whether you sit correctly at the moment, and it beeps when you're having the wrong posture. There's stuff in your socks that measures your temperature and body temperature all the time. This is just some super simple example that have been around since many years. But these days, even in whatever crossing you're going over, there will be most likely some camera somewhere that is at least measuring number of cars going through or even other stuff. So there's everywhere sensors, everywhere cameras, everywhere whatever you can imagine. And obviously also more implicit sensors that are measuring, for example, stocks or whatever else you want to call it. So say from the economical or financial side. So there's data and sensors and everything everywhere. And one idea of data science is to make use out of this data. So if you would ask, I guess, the Delphi people, what's the vision of the future? Of course, it's hard to say. However, at the end of the day, big data, so all these large data sets, and what we call real-time analytics, which is one part of data science, will definitely be crucial in the future. And I left now out the next slide where I had all these different data sources and data domains you can think of, because you all have your personal data domain probably on the top of your head. So in which particular domain of the world you would like to look into data or use data or whatever else. So speaking of health data, speaking of social data, speaking of what we heard in the beginning, artifacts or items in museums, whatever that is, it is part of this whole dataverse, or whatever you want to call it. Good. And the main question is then the thing at the bottom of the page: how can data science actually help here? And yeah, again, what actually is meant by this? Good. So going from data to the whole data science thing, maybe it's time for a first try of a definition. At the end of the day, what we are meaning mainly by data science is you're having data. Well, I think that became clear. Then there's some so far undefined circle or bubble of this data science thing. And now it becomes important, because what data science gives you at the end, and this is what it sets it apart from normal, I look at my data and just are happy because it looks nice, is data science usually creates what we call actionable results. So the point is not only the data science says, okay, there is maybe some trend in your data, or there's some anomaly, or there's something weird happening or so. It gives you at the end something that is actionable. Now, what do I mean by that? Let's take a super simple example that I stole from this webpage that I showed you down here. So it's even old, but doesn't matter. The point is the following. If I look at my watch, for example, I have one of these fitness tracking watches, and it tells me I took 7,000 something steps today. Then this single number is fairly useless. Is it a lot? Is it too little? Do I usually do more? I need context, right? So now the point is that if I add context to it, for example, the trajectory of the last couple of days and what I usually do on a particular day, maybe even with the times that I usually do it. So this is a little bit depicted in these two graphs here. Then I have my data. I have some information. From this information, I can now get insight. In this particular way, I know that to reach my goal at 10,000, that's a dashed line here, I need another 2,500 roughly steps to reach my daily goal. So the insight is I'm missing 2,500 euros would be good. No, steps. The other insight is it's already almost 5 p.m. So there's not much time left to actually get these 2,500 steps. So the action, and that is now the point, the actionable insight is, all right, if I want to get my aim of 10,000 steps a day, I need in the next couple of hours to do my 2,500 something steps. So it's actionable, right? It's not only something, okay, I got information, I can even do something with that. And this is the main pattern, which you can now apply to all the domains I mentioned earlier, to health, to finance, to economy, to social sciences, to whatever you wish. The point is always, single data might not be too important. Data science also creates this context, identifies some insights, and these insights can be then put further to be actionable. That's the whole business, basically, what usually data science is about. Another example, also super old, you might have heard about it, but I love it because it really gives you the power of data science. Some people might or might know Target, a really large reseller in the States, but you can basically connect it to any bigger market type that you know, also in Europe or Germany, even if you want. Now, why Target is coming up in this example is because Target was well known for having these vouchers. So you can even see here again from the dates that these examples fairly old, but the same thing still applies. And in particular, Target has had these, again, domain, if you want, or topic-specific vouchers. So they had it for, well, today it's about bedding, bath, and indoor furniture, and rugs, and I don't know what. And then there was some store-wide. And they had, and that's what the example is about, they also had gift cards that they sent to people, and that is now the point, who potentially would expect babies. So they would send these things or on a particular ground that I'll tell you in a second. And that's the point of this example. So they have this, right? They have vouchers that they send to people where they think they expected it. Now, one day, an angry father runs into a Target store somewhere in the States. So he asked for a store manager and yelled at the person. And asking, and now that's a plot twist, why his teen daughter forgot about the age, but you can read it actually still online somewhere, got then these coupons, these baby coupons. Some days later, and then left the store, I guess, in a rage. Some days later, he comes back and apologizes because he learned that his teenage daughter was indeed pregnant. Now, why did Target know about this and the father didn't? And the answer is in data science. Of course, what Target did was actually quite easy, and still is true and is actually quite often used these days. They looked at data. So Target has a particular client program. That's what one needs to know. So the point is, whenever you buy something, you show your coupon card or whatever card they had there, and everything you buy was then tracked with this card, so that at least some basic information about the person, I guess age and gender and so forth, and what they bought. And the point is that with this data science approach that this Target team did is that they identified a set of particular products, in this case, a set of 25 particular products, that when they were in combination bought, in a particular combination, there was a quite high probability that that particular person, in this case woman, was indeed pregnant because they had also information that they came back and really bought their baby products. So they could even, based again on the time and the types and the combination of products, connected to the particular time. So in this case, the trimester the woman was in. So they could, at least in principle, approximate even the due date. And with this, they could just sample the databases, and whenever there was another hit, as in like another woman bought this particular combination of products, then they could say, bingo, send them these vouchers, and the best case scenario, convert this to the woman coming back and buying something in the shop. So from the perspective of data science, super easy. I will give you a couple of examples later how this can be done, but super effective. And this is really one of these ideas that data science stands for. I can analyze data. I first need to get data. I can analyze it, and then I can connect it or convert it to something actionable. In this case, well, I can maybe in the best case scenario, increase my settings through sending out the right vouchers in this particular case. Who wants more about it? I think this is still the right link down here where you can read a little bit more. However, when you do this kind of analysis, you need always to be at least aware of one very important thing. There is something called correlation, right? If I buy something that correlates maybe to being pregnant. Correlation is 100% of people who breathe do die. It's a correlation. A causation, so what actually causes something else is, well, 100% of people who don't breathe die. That is the actual cause. However, the correlation is still true, but it's obviously nothing that is in any way interesting, and in some ways might even be wrong. There's a clear correlation, for example, connected with the global average temperature and the number of pirates. And you can see it, and even with NeoData, there's a very clear correlation, but it's definitely not a causation. So oftentimes, if you analyze data and look at data, you will find a lot of correlations, but maybe some of them are either wrong or, well, trivial or in other ways misleading. So whatever you do from today's lecture or webinar, maybe this is one of the things you might want to take away, that there is something called correlation and something called causation. And obviously you're interested in causation. Good. So these was the motivating examples to show you, okay, that might be an interesting topic, this data science thing. Good. Let's go a bit into more details. So as usual, one starts these kind of blocks with a little bit of history. Also, I don't want to bore you too much with that, but because you probably will get the slides afterwards, so you can have a little bit of a look later on. So this is more or less the time periods that people, if you browse through Wikipedia and other sources that they give you. So there was empirical science basically before 1600. So, let's try out stuff and then find out whether it works or not. After 1600, people started to grow theoretical components in physics and in math and so on and so forth, and also many others. Then starting with the 50s, maybe a lot of these sciences also developed some computational branch. So computational ecology, computational physics, computational mathematics, and so on and so forth, where then with the help of computers in that case, even other more complicated or complex analysis could have been done. Started in computational science mainly with simulation. So you can find something that you cannot compute anymore, for example, in mathematics, or you have a particular complex system in physics that you would like to simulate and see what's happening after some point in time. Game of Life is one of these things that are quite popular from that area. And then round about the 90s of the last century, always sounds scary, basically what we call today data science was more or less born in terms of a lot of new data types coming from, or data types coming from instruments, scientific instruments mainly, but also sensors actually were or became available, were available also on the called internet back then, such that there is just a lot of new data that people could play with or even use it for scientific reasons. And that second thing that was then playing a major role was that actually storage became cheap. So before that, it was quite expensive to actually store data. Think of these tapes and these disks and whatever they had back then. But beginning of the 90s, middle of the 90s, beginning of 2000, definitely hard disk drives became comparatively cheap. These days, they cost almost nothing. It's of course not true, but for the size that you get for $100 or 200 euros or so, it's just unbelievable. So at the end of the day, this was one of the main reasons why people could collect now this data and make it available through more or less public domain data sets. So everybody who was interested in that could collect and use the data that he was interested and do data mining or data science on it. So it was one of these big drivers that were happening. Good. Yeah, another definition of what data science really is to say, well, I'm solving problems with data. And what I did here is to put you a bit more of this so-called pipeline that one could understand data science really is. So at the beginning, usually it's a problem, or maybe you're just curious and then might not really have a problem, but you have hypotheses or whatever you want, a scientific goal, something. And that usually, and this is then the next step, otherwise not data science, that needs to be connected to data. So I might need data to analyze something, I might need data to find trends in something, but need to be data about something. So if it's just a theoretical problem there where no data is involved, it's not data science. Once you understand your problem or your question or your hypotheses and which data you might need for that, or even where you're going to find it, you go to the next step, which is collecting and understanding the data. So either there's already a data repository or a data set or whatever else that you can just collect or use, or you need to scrape it yourself, it's called. So you have something that you can send to the internet and then it copies it from website, from newspapers or stock markets or whatnot. So you get make your own data set basically. And then you also obviously have to understand this data that you either created yourself or downloaded from somewhere. Then super big step in this whole data science process is cleaning and formatting data. And you would probably, if you don't know already, believe how much time goes into that. That will be on the next slide. And once you did that, well, then you actually can use the data and the algorithms or the methods or the models to actually do the analysis and maybe create a solution to your initial problem. So I guess that sounds super cool to you, otherwise you wouldn't be here. And then the next question is usually, okay, cool, but what is the skill set that I need as a data scientist? What should I be at least a little bit familiar with such that I can start in this direction, or to understand where I do have some gaps and might want to actually include a bit more of knowledge or collect a bit of knowledge to become a better data scientist. Yeah, the scribbling I actually tried out earlier. Sorry, don't take that so serious. The point is you will need a little bit of understanding of mathematics and statistics, because there will be a couple of trend analysis, say statistical analysis, is a result significant? So is it actually most likely true at least, or the evaluation that I do with my data and my method, is that promising? Is it good enough? Whatever enough means at the end of the day, we will go through a couple of these things in the next sessions. Hacking skills is because I didn't want to write programming. I don't think these days you need programming skills anymore. I think in the age of these chatbots and these I help you to program kind of websites, everybody can program in some way. But you need to understand the underlying ideas, or you need to have this idea of, okay, I'm able to do something with the help maybe of something else, whether it's a human or a program or a bot. But you need to want to be this hacker. And by hacking, I don't mean hacking computer systems, but putting together things that work at the end of the day, understand at least the idea of why it works, and be able to get the evaluation right that you can prove more or less that it works. But again, it's not necessarily anymore to be a real programmer here. And also that we will do in the hands-on session, where you will not learn to program. That would be a little bit too much for a session, but you will learn how to get scripts together and put components together, make them run in some more or less planned way, and then get results out of it. And what I mean by expertise here is domain expertise. So for whatever domain you're interested in, whether it's social or mathematics or physics or economics or you name it, you need to be able to understand what's going on there. So what will never work is you find some cool data set, you like the idea, it's not your field, you do analysis, this will never work. You need to be maybe not an expert, but quite well in that topic to obviously come up even with a good question and understand the data about it. Not to talk about the results that you can interpret and make a story out of it. Story in the way of, this is what the data tells me. Again, this is super simple, super simplification, but this is more or less the three main pillars on which the whole data science rests on. You might have guessed already, or you know. If not, I will tell you now. So which of these steps are the most time-consuming and might or might not come as a surprise? This clean and format data and collect and understand, these two things here maybe. This usually on average takes 60 to 80% of the overall project time. There is a long lecture that I'm usually giving in these classes where I'm explaining why this takes so much. To make it super short for you, because the data has errors and gaps and is never complete, and the people have the complete data take ages to respond to your calls and so forth. So basically, whatever you do until someone else cleaned everything for you already because she had the same question, looking at the data, organizing the data is really the most time-consuming step. Once you have all the data in shape, the rest is more or less standard. Sometimes you need to come up with a little bit of different things that people usually do. But at the end of the day, if the data is in a good shape, the rest is not that hard anymore. So always keep that in mind if you're talking about data science or data-oriented projects, that the data is the main asset in this game. And much more time consuming than everything else together, basically. Okay. However, which steps are the most challenging? That's then the other part, obviously. So, I mean, collecting data is probably not that challenging. It just takes a lot of time and it's tedious and it's annoying. But from a perspective of, okay, but where of these steps do I need to invest most of my smartness into, if you want it that way? Then this will be obviously the last part where it's about the analysis itself, or to use the data to create some solution that hopefully answers your initial question. And this is usually going hand in hand with either a little bit simpler data analysis or a little bit more complex, maybe not necessarily complicated, but often more complex, called machine learning. For both these, I will give you an example in a minute, and also then over the next 2-3 seminars, including the hands-on sessions, we will dive into a little bit more complex example also. I'll show you how to do this actually hands-on. There will be some simple data sets that we will be using, and you will then hack together, as I said earlier, the solution, and hopefully we'll learn something about your own use cases in the future, how this can be done, or at least where to look for help. Okay, just keep in mind, data analysis and machine learning are at the end then the most challenging steps, but also these that will determine whether or not your project or your question will be answered. Data analysis. Data analysis, obviously relies on data. So again, everything can measure or record or find somewhere. And then, and that's the interesting part, most of this is about statistics. It's not so much about, well, that will be next step, machine learning kind of things that you might have in mind, but it's more really about statistics that was invented in the 50s and 60s, maybe 70s. So from that perspective, quite old stuff, still very efficient. Think of this target example earlier. This was more or less pure statistics, not much more, to be honest. So it gives you, at the end of the day, the main characteristics of the data, and in the best case scenario, it becomes actionable. Your sales are too low, you need to increase. From this perspective, there's coming too little of information about this and that. You need to increase it, otherwise the result is not good enough, blah, blah, blah. So there's a lot really going down to this quite plain, a little bit more advanced today, but at the end of the day, quite simple statistical summarizing. And then the last step in data analysis is then also a little bit more towards the algorithmic perspective. So there's usually some kind of standard algorithms. Again, these pattern analysis, for example, that in the target case, which of the products are then the ones that are connected to pregnancy. This is usually coming in algorithms, which are also quite standard. There's usually a kind of library that has 20, 25 algorithms. And once your data is, as I said, in shape, and you did some of the basic analysis of statistical case, you can apply these algorithms because then you know which one would work, and then you get your results. So the process for data analysis is more or less this, what's written down here in the orange box. It involves exploring data to extract insights, often relying on statistical techniques. Again, the more or less old school stuff, but still effective. And it usually uses predefined algorithms to make sense of the data. And again, also in the next sessions, we will go through some examples in more depth, but I also have 2-3 examples that we will go through in a minute. Good, that was data analysis. Now, what's machine learning? That was the second part. Machine learning is a little bit different because it's really about creating, or hopefully using, models that are learned from the data itself. So it is not necessarily anymore a model that I get from a library or an algorithm in that case that someone else has defined, statistical in the nature usually, but the model that I need is really connected or learned to my very particular data set. So it's really using the information that's in my data. So at the end of the day, it's not super different, but it's only trained or learned from the data I have in hand. That's the main difference. And at the end, I also need to come up with another component, that's the evaluation component here. So if I learn my own model that is usually only connected to my own data set, well, then I can't use standard techniques to evaluate it. I need also to connect this evaluation to the model that I learned from my data. So the process is a little different now. So the focus of machine learning is to really creating models that can then automatically learn or are even learned in full from my data, and therefore can also improve over time. My data changes, also my model changes. And in most scenarios, at least, that even comes without explicit programming. There's some programming or hacking in the background, but usually it's not that I have to really program code that my model, that describes my model, but it's really there's some kind of model from somewhere, and I just throw it at my data set or at my data and say, well, learn. And then it comes back with something it learns. And then with these results, we can check whether it, first of all, learned the right thing. And second of all, then we, in the best case scenario, again, get insights that, well, we learned it are actionable and help us to reach our goal that we set in the beginning, or to answer the question that we formulated in the beginning. Good. So the two options, a little bit oversimplified, of course, but that you can see the main difference. So data analysis is usually you start with the data. Obviously, that's always the case. And you started with a program. So you need this algorithm that you are having in mind that gives you more or less something that you need. And both things you feed a computer with, and then an output comes out and gives you these insights about the data, for example. And machine learning is more or less the idea, okay, dear machine, I give you some data. I give you also some output. For example, this is a ship, and then you show it a picture of a ship and the name ship. This is a cat, you show it a picture of a cat, and you give it the name cat, and so on and so forth. And you tell the machine to learn a model that creates these relationships, because what you showed at the beginning. And then the thing spits out a program, if you want, or a model. So it's different. So here the model, the program is learned. Here you start with a program, you know what you want to analyze it for. You give it again some kind of data to do the evaluation now, and then your new data, maybe your machine again goes and does something and tells you output. And again, now it might be able to learn, for example, what dogs are, if you showed it cats and ships before. That's the idea that's under this machine learning umbrella, that you don't really necessarily at least program something that you know from the beginning how it works, but you give it more or less an idea of what it should learn, and learns it itself, and then gives you something that you can work with later. And again, also here, stuff like deep learning or artificial intelligence and these kind of phrases are around since many decades. And also here we will look a little bit into in the next couple of weeks in the webinar to give a bit more of insights and depth here. But again, the main understanding or takeaway from this page is traditional or more traditional, more classical data analysis. You have your data, you have a clear idea of what you want to analyze it for. You have the program that you feed your computer with, and you get an output. You could say, hey, here's my sales, and here's the weather, for example, or the temperature. Please find some kind of relationship. And it comes back and says, oh, when it rains, you sell more umbrellas. But that was also more or less clear at the beginning. But you told the program to look for something, a trend or so. And here you give it really only data and some output or labels, as we call it. And the thing learns the model itself. And then with the model or the program learns, you can also answer questions. So this makes sense if you have super complicated data and you have an idea of what you're looking for, but not necessarily how this is done. And in the upper case, you know more or less exactly what you're looking for, what you would like to analyze it for. And therefore, you can already define the program that you need, and you just run it and then get some output of it. So that's more or less the main difference between these two approaches. Good. Yeah, so machine learning is creating and using models that are learned from data. There's some classical examples. So for example, this was one of the first machine learning applications in the 90s by some guy called Yann LeCun, who was back then professor at in France, at the university, to be honest. But now he's head of a data science team or machine learning team at Facebook. And he was really one of the people who pushed this whole neural network idea, what today know as deep learning, really much forward. One of the fathers, if you want to call it that way. And then there's multiple other examples that you could, if you wanted to look for on the internet, from predicting traffic volume at particular rush hours. So what Google Maps is doing, if you tell it, okay, I want to go from A to B, give me the best route, even not only on the current status, but also on what you predict from the data you have seen in the past of how this road will look like. And then maybe you see there's a construction site somewhere, and you know that this will influence the other roads in a particular way. So it's not only, I know on Sundays the streets are always full, but I know, okay, over the last couple of Sundays it was a little different because there was a different situation on the streets, or there was construction site, or well, today doesn't seem to be as bad as usual, therefore my prediction will be different. So it's not only really interpolating from what has been seen, but really using all the information that is available and putting this into a quite complex model in some way that is learned from the data. Credit card fraud and all these kind of other things is a lot of, yeah, just to say a few more examples. There's hundreds, I would say, even out there that are really quite famous for this idea of what machine learning can do these days. Good. Now, one of the main topics was obviously now this idea of, okay, I have data, I want to learn from data, so how do I do this? So in the remaining 20 minutes, I brought you 3 examples that I would give you at least try to give you a glimpse on of what this really means. However, before we do that, just one more comment about where does data actually come from? Because I talked a lot about now, well, we need data, you can use data to do something, but what is this data? And there's more or less 4 or 3 larger categories. One is internal sources, so either you are a business company, or you are a scientific company, or you're a museum or whatnot, or a research group. Then you usually have something internal, some database, some artifact, some business databases, some experimental data, or whatever else. This usually is internal sources. Sometimes you have internal sources, but actually need external sources, or because you just want to do some analytics or some science or develop any methods, and then you will usually rely on existing external sources. So you could look at, for example, you want to predict the stock market because you want to invest your money better. Then you might look at external available stock market data. Or you are trying to get a cool restaurant around you and you want to build a method that gives you the best restaurant around you based on some reviews. Then you might actually go through hundreds and thousands and millions maybe of reviews that you can analyze and build your own data science tool such that it gives you the best restaurant around you based on some reviews. You can learn this, for example, and so on and so forth. And then obviously, well, you can collect and create your own data. This is also what WiNoDa is about, partly at least. But this is obviously beyond the scope of this webinar. And one just word of warning, if you look at online data, so these things, what I said earlier, stock market data, whatever, and so forth, this usually comes from APIs or application programming interfaces. And the only word of warning here is sometimes it is possible to get this data. So Facebook was quite a big thing, say 7, 8 years ago, where Facebook allowed you in some way to get data through this API. And that meant that, for example, I could automatically go through all the profiles of my friends and sometimes even of the friends of the friends, which was back then not a big deal because no one was really that eager of looking at user rights and whatnot. And still, it was technically possible, but it wasn't allowed. So Facebook told you in the agreements that while it's possible, you're not allowed to do that. Same was for Twitter and many others. Oftentimes, you are able to get data from the web, but you're actually not allowed to, which is a little weird. I understand that. But the only point here is if you're scraping data from the web, you might violate licenses under this data is given away, if you wish. So the license might tell you, okay, you can look at our data if you're using our service, but you're not allowed to use that data or download it for your own purposes, although it's technically possible, right? Technically, you can extract all the information from any website that you're seeing, but they might just not allow you. So just a word of warning here, when we talk about data, oftentimes data is not necessarily allowed to use, although you could, in principle, do that. So the main point here is not all data that's accessible is actually good to be used, either from perspective of it still might be wrong, you never know, but also from the perspective of, well, always check the license and privacy concerns or some fee that you might have to be paying when you're using the data, if you actually want to use it really. Good, but just as a word of warning here. Now, I have to quickly switch from my keyboard to my pen because I've learned some cool seminar that sometimes one should not only talk, but also actually draw something cool, and then people become more interested. So I have now 3 examples of why or how learning from data actually works. There's 3 simple algorithms or examples that I have here, standard textbook stuff. But I just want to show it to you to give you a little bit of a feeling what again data science in the wild actually really means, and give you also the rough idea that the whole I need math, I need statistics, and so forth is, well, in principle true, but usually it's really intuitive and easy to understand. Now, let's assume we have some, well, super simple. We have some data that usually comes in some kind of database. So this is not very nice, but again, it's supposed to just show you what database looks like. This, I guess, yeah, doesn't matter. That's a database. Then I want to do something with, that's the part we're talking about now. So some algorithms, some analysis. And then I want to have, maybe in our case, in this moment, some kind of prediction. And with this prediction, I want to be then able to, that might be some insight that I need. And this, in the best case scenario, as we said earlier, is actionable in some way. Now, let's assume that we have data about houses. First, because I can draw houses fairly okay. So with data of houses, we know usually the house price, maybe say in euros, might be some external database, or just because we have a really good idea about what a house would cost. And for each of the houses, we have some, let's call it features or properties. And that could be the square meters, that could be the number of rooms, and so on and so forth. Okay, and if I now put this information about these houses in some kind of chart, let's do a 2-dimensional one, and on the up axis, I basically put now the house price in euros, and on the left to right horizontal axis, I put now the, let's keep it simple, the number of square meters. And I do this for every house, and for every house I put a dot there. Then my data might look somehow like this. So this is now all, so if I have a house, so let's say this is 100 square meters, and this is, well, these days, I don't know, let's make it simple, 100,000 euros. Then I see, okay, the more square meters I have, this is what is becoming more or less obvious, the more expensive my house becomes. And now what a algorithm from data analytics or the data analytics part of data science would be is it would put a line through it that is having, not the best line ever, but that is having the least distance between all these points. So maybe that's a bit better. And you see now, if you have a house that you want to sell and your house has, let's say, what is it here, 200 square meters, and then you connect this line to here and then bring it over to here, then you can more or less understand, which in this example was quite simple, what the price of your house actually would be. So just given some data that I collected somewhere and drawing this regression line, that's called, into it, I can now predict house prices. So even if I don't have some data in some of the regions, so here wasn't too many points, I can still, given this model or this program, I can more or less predict what my house would be worth. And this is called regression, or actually really simple regression. And it's one of these programs or algorithms that I mentioned earlier that is used in data science to actually do some more or less quite simple statistics. And as you can see, there was not too much magic here. I just put something in some two-dimensional chart, drew a line through it, and then I was able, in this super fake example, of course, simple example, to predict what the house price could be. Now, of course, I cheated a bit because I only looked now at the square meters and then the price in euros. So I omitted everything like number of rooms or locations or whatnot. But this is then becoming more multi-dimensional. So I get then the idea of multiple parameters or multi-dimensions, which I can then also do there. And then I can draw it a bit more complicatedly in 3D and 4D, 5D. Still not really able to draw anymore. However, you get the point. From the basic idea, you can now extend it to something much more complicated. And at the end of the day, have something that is now, in whatever way you are using the question here, be able to predict you something, to give you more insights, and the best case scenario, even to make actions out of it, sell your house or keep it or whatever, buy houses if you're a house seller. Second example is classification. One thing I forgot. What we have here is something called supervised learning. Supervised because I told the program everything it needed to know. So I told the algorithm, look, this is the input, that's the output. So I was kind of like a teacher. I told it everything it needed to know. And you've seen also at the end today something which is called unsupervised, where I might not know the answer, just the data. But in this case, it was something called supervised. Okay. Second thing is called classification. In some way a little similar, but in the case before, the output that I was looking for was indeed a price, right? The price was ranging between, I don't know, €0 and maybe €1,000,000. So it was a particular number that I was looking for, so a real number. And in classification tasks, it's not really important which number it is or that it even is a number. I'm interested in classes, hence classification. And the class could be dark, light, larger than 10, smaller than 10, good, bad. These are classes. Can be two classes, can be many classes. It's two classes called binary classification. Again, some stupid example. So we have, again, our data or some database in some way. We want to do something with it. And then again, we want to do some kind of prediction. But this time we want to predict the classes and not necessarily the house price or the number anymore. Okay. In this example, we do something, again, super simple and maybe not intuitive. And we are collecting reviews about movies. So we have reviews that we get from Yelp, or can be restaurants, or can be anything. Can be also restaurants, doesn't matter too much. Anything where we get our hands on review data about something. So we have reviews, say, movies or hotels, whatever you wish, doesn't really matter. And now we know for these reviews how good people rated something where they wrote a review about. So they said, this hotel is fantastic. I love the look through the mountains, whatever you wish. And then they usually give these stars, right? 0 stars, or can you even give 0 stars? 1 star for not really convincing, to 5 stars. Well, that's the best. So you have some text written, and you know, okay, cool. This person here gave, let's say, 4 stars. So it's clearly something good. Then you have another review, and the person says again something. Oh, the look wasn't that good. The heating was cold. The bed was weird, and the bathroom was not very nice. So the person gives only 1 star. So clearly we know in this case, wow, that's a bad review. So it's a bad category. And then maybe just for the sake of the example, again, there's another review that comes with 3 stars. And we also say, okay, that we consider to be actually from the good category. So now we have data, and the data is in some way connected to a class. So we have the text basically, we have the class, good or bad. And again, with this kind of data, we can also draw some kind of diagram in some way. And now we can put all the reviews that are based on some keywords maybe that we extract and that we can connect more or less clearly to the number of stars. So we say, okay, whenever it's a positive category of the review, that person uses the word great or something similar to great. And when the person says something bad about something, then the review contains also something bad, maybe the word bad even, or the word unbelievably bad, or whatever it is, 2 words. Anyway, you get the point, some adjective that is somehow negative. And then what you can do is that you now connect, or again, put somehow as much as you think this word you're looking for is strong, you can now put into also this diagram, and every of these symbols here now is connected to one of your reviews. And then you do the same with the other reviews. So whatever you think, they're on these axes. So if you think the review is more on the great side, then it's somewhere more here. And if you think the review is more on the bad side, well, then it will be a bit more up in some way. And now it's quite simple. You just now need to find the separating line through it. And now whenever you get a new review, you put it somewhere in this chart, and you, for these 2 dimensions that you have, so you have words for bad and words for great. And if you have more bad words than great words, then will probably be the unknown review, if you wish, will be somewhere here. And now you only need to look to a diagram. Is it left from my classification line, or is it right from my classification line? So this review is then more or less on the bad side. And if you have a review that contains more good words than bad words, then it will be somewhere here maybe. And therefore, you know, okay, that's a good review. So you learned, the only thing you learned before is this line here. And you learned, okay, I need 2 dimensions in this way. So I need the number of bad words maybe and the number of great words. And only with these 3 things that you extracted from your data, you found this line. And the next time you get an unknown review, you just say, count the number of bad words and the number of great words. You put the dot accordingly, and then you know, okay, it's either left of my classification line or right of my classification line, right? So again, same thing, but now you didn't say, okay, I want to get a rating back, say 1 to 5 or so, but I just want to understand, is it a bad or a good review? So again, that was supervised because I told my program or my algorithm everything I knew before to train it, and then afterwards I can again use it to predict something. So here the algorithm that we used is classification. Classification. Also, as the name suggests before. Good. Last example, very short because we are having only 3 more minutes, but that'll be enough because it will be the same pattern. And I only give you the rough idea to it because that's also something where I just want you to understand, okay, that's another class now of algorithms in some way. Again, we have some data, and this time our data is articles, say scientific articles. So we have scientific articles. You could also take reviews, doesn't matter, but for the idea of the example. Let's say we have scientific articles. And that's now the point, I have a machinery that gives me the answer to how close together are two text, in this case articles, based on, say, word similarity. So if they share the same words or the same from a dictionary, though I know how many words exist, and if they have more than 10 times the same word or so, then they seem to be closer to each other or similar to each other than others. And if I define this, what we call metric, so that you have for two articles that are similar, you have, for example, the metric, okay, there's a 1, and if two articles not similar, there's a 0. So you have the idea of, I give you two, if the two articles, it tells me how similar there is between 0 and no, and 1. Then I can group now articles. And this is called clustering. So I'm clustering based on the idea of how similar two articles are. And that's more or less everything I put inside the algorithm. I tell, okay, look, here is a lot of text, different texts or articles. Here's some manual of how to judge whether two articles are similar. I give you the option to give me a number back between 0 and 1, 0 not being similar at all, 1 being totally identical. Please group all my articles together, which are similar, and tell me also the number of groups at the end that you have. And then you can say, okay, cool. I put you one article after this has been done. This article here, I like in particular. And then you can say, okay, cool. Then from the group that this article was in, give me the others. And then you get articles that are similar to the one you like. And then maybe you find something closer to your research question also, just based on this clustering idea. And that's what is then called unsupervised learning. Supervised. Because I didn't tell the algorithm in the beginning which of the articles are similar, which are not. I just gave it some metric in this case that says, okay, two texts are similar if this is the case. They share the same words or whatever else they are, the same length or I don't know what. And just based on this information, told it, okay, and now group me everything. And once you group it, I can say, okay, cool. Since I like this one, I can also get some actionable insights. In this case, okay, I should also read this once they are in the same group because they might interest me because they're actually from the same type or content or method or whatever I like. So that was then the clustering, which is a algorithm of the unsupervised case. I didn't give it the results or the learning. Good. And with this, it is 1 o'clock, so we are done. Give me 25 seconds for the summary slide. I showed you more or less, at least, the data science process. Here's also a nice article where you get a lot of more details on a good level actually explained. So I have some questions in the beginning. I have some understanding of data. I prepared. I do some modeling, evaluation, and deployment. Deployment meaning give me these insights in some way. And based on that, you can then go through these 3 boxes here mainly. So data science, and that's one of the points, is forward looking. So in the most cases, we are looking for something for predictions that lead to some action. And the best way then this is the basis for some insights that are actionable in terms of I can do something with that information. The second thing is that data science enables timely data-driven decisions. So decision makers usually have all the data that are currently available at their fingertips, and therefore, based on the data that they see now that is describing the situation now with whatever data sources you know, can be used for the analysis. And last thing, data science integrates really complex data. That's what I tried to show you a little bit with this house example, for example, where you said, okay, it's not maybe only about price and size of the house or square meters or so, but there could be also a lot of other like location and maybe the weather and time zone and I don't know what, and everything can be integrated. And then the decision can be based on super complex things that are sitting in your data and that you're trying to get an idea about. Good. That's it for today. 1 minute over the top. Sorry about that. I hope you learned or got some ideas about something. And if you like this kind of webinar and the ideas that are put forward today, and you would like to go into more details, then the next couple of sessions are for you. If you have questions, you can always mail me as we discussed. And I wish you a great rest of the day.